Hey everybody, welcome to Environmental Organic Chemistry with Dr. Lisa. I just got this snazzy new microphone for Christmas, and I'm recording with it, and I think the audio is going to be much better now. Yay! All right, so this is just an introduction to kind of give you an idea of what this class is about. Why are we here? What are we doing? What are we hoping to learn from this semester? So what you see in front of you is sort of a stylized schematic of what we think the world looks like, what an environmental chemist thinks the world looks like. It's divided the world up into little pieces or boxes. Up here we have the troposphere, and down here we have the water column, and we have some gases and particles in the atmosphere. We've got rain coming down. We've got sediment at the bottom of this little lake or river here. We've got the terrestrial ecosystem. And if we release a chemical to this world, the question is, what's going to happen to it? Where is it going to end up? And what's going to happen along the way? Is it going to react or be destroyed? Could it react abiotically, or could bacteria maybe eat it and biologically break it down? And does the point of release make any difference into what happens to this chemical? So, here it's showing some anthropogenic sources, and these are all shooting the chemical out into the atmosphere. The troposphere, of course, is the part of the atmosphere that's down here where we live. So if you release something via a smokestack, or, just the chimney on my house right now is releasing CO2 and other gases and other chemicals out into the atmosphere, the troposphere. And while it's there, a lot of things could happen. There could be some reactions with things like the hydroxyl radical and other chemical reactants. We'll learn about those toward the end of the semester. And then there's also just some physical processes. So the chemical can partition between the gas phase and the particles and the water phase, the rain or snow. Some of those, like the particles in the rain and the snow, will get deposited back to the Earth's surface here, so that's going to remove them from the atmosphere. But the stuff that's in the gas phase might persist in the atmosphere for a long time, and therefore, because it persists for a long time, it would have a long time to travel. So things that stay in the gas phase travel very long distances. By the same token, if I release something here on the terrestrial surface, maybe it's an antibiotic that I give to cows, and the cows poop. The poop goes into the terrestrial ecosystem, and eventually some of that stuff can get mobilized. It can end up in the runoff, and it can run off into the aqueous system, a river or a stream or a lake. Or it might just stay in the terrestrial system. It depends on how soluble your chemical is, whether it can be dissolved or partition out of the poop and into the water and then just, run off, or if it sticks to smaller particles of poop that get broken up and then washes into the waterway in the form of a particle. Once it's there, it will partition between the dissolved phase and the particles in the water. And particles also could include dissolved organic carbon, which is not really a particle because it's dissolved, but it's organic carbon. So we think of it as a phase that the chemical could partition between. So in the water column, the chemical gets to choose between the water, the truly dissolved phase, the small particles floating in the water, and the dissolved organic carbon. The particles will eventually settle. Right? Sedimentation, sediment burial, they'll eventually settle out of the water column, and so that will remove them. But the DOC and the dissolve phase will stay suspended in the water. But if it's in the dissolve phase, it might volatilize out over here via gas exchange with the atmosphere. And also, of course, there's the possibility that it will get its way into the food chain. If it was an antibiotic you gave to cattle, it's already in the food chain, and then we can ask lots of questions about what happens when people eat the meat. Does the antibiotic stay in the cow? Does it just get excreted? Or does it stay in the cow and therefore I'm exposed to it when I eat beef? If so, what happens inside my body when I eat the beef? Does that chemical then stay in my body, or do I excrete it? And in the the aquatic food web over here, then we can ask lots of questions about how does it get into the aquatic food web? What does it do once it's there? Does it bioaccumulate? Does it biomagnify? And so, for example, if we think it biomagnifies, then it will build up to pretty high levels in the piscivorous fish. Piscivorous means that they eat other fish, right? Pisca. I think it's Latin, right, for fish. So piscivorous fish are fish that eat other fish, and so they're high up on the food chain, and they might build up high levels of these chemicals, and then if you eat fish, you will then be exposed to high levels in your food. So all of these processes depend on the chemical structure and the physical chemical properties of the chemical. And that's what this class is all about. It's about being able to look at the structure of a chemical and tell something about how it's going to behave when you release it to the environment. So here's an even more simplified version of the world. And this is it's a diagram, it's a sort of a schematic of the processes that were incorporated into the transport and fate model that was used to predict PCB concentrations in the Delaware River. Because the Delaware River is one of the few rivers in the United States that has a TMDL, a total maximum daily load, for PCBs. That's the regulatory limit of how much PCBs you can dump into the river and have the river still meet the prevailing water quality standards. So this is required under the Clean Water Act. And so they went ahead and devised a TMDL for PCBs in the Delaware River. And to do it, they had to have this big complicated model. So the PCBs are regulated as the total amount of PCB in the water column, right? And so that includes the dissolved PCBs. It includes the stuff that's bound to dissolved organic carbon. And it involves the PCBs that might be sorbed to organic carbon, either in this particular model, they did something a little unusual. They divided the particulate carbon in the water column into what they call detrital carbon, which means it's dead, and biotic carbon, which is living. Biotic carbon is basically phytoplankton here. And the difference between the two mathematically in the model, the difference is that the biotic carbon settles more slowly. So the dead carbon settles quickly, the biotic carbon settles much more slowly. Okay, that's unusual. Most models don't make a distinction between the living and the dead carbon, but in this model they did. So all of this stuff, all of the water column, the sum of all of that is what's being regulated in this model. But in order to figure out what those concentrations are going to be, you had to, I'm going to erase all ink on slide here. There we go. In order to figure out what those concentrations in the water column were going to be, you had to model all of the other compartments, the surface sediment, the deeply buried sediment. And you notice the difference between the surface and the deeply buried is that the burial only goes one direction. This sediment down here cannot be resuspended back up, right? That does not happen. No. Okay, so that's the difference. So there's surface sediment, there's benthic sediment, then there's also inputs. Here's from tributaries, point sources, atmospheric deposition, volatilization out to the atmosphere, transport from one box of the model to another, and eventually out into the Atlantic Ocean. So all kinds of different processes going on here, and all of this has to be modeled in order to come up with a reasonably accurate number for the PCB concentrations in the water column, because that's what's being regulated. So then you have this model, it's perfectly calibrated, and then you do a loading assessment and you say, how much PCB can I dump in the river every day and have it still have this concentration in the water column down to a low enough concentration that it will meet the water quality standard. That's how you do a TMDL. And that is what we're going to do in this class. I mean, obviously a very, very simplified version, but we're basically going to calculate a TMDL. How much of a chemical can you dump in the water column and have it still meet whatever the standard might be, some target concentration. And again, all of these arrows here represent processes, right? So this is a partitioning between the dissolved phase and the DOC. We have partitioning back and forth between the DOC and the sorbed phase. We've got settling and resuspension and diffusion. All of these processes depend on the physical chemical properties of the chemical. The amount of the chemical that stays dissolved versus the amount that's bound to DOC versus the amount that's sorbed all depend on the physical and chemical properties of the chemical. And so when they did this model, they had to input information about the Henry's law constants and the octanol water partition coefficients and things for PCBs. And that's what we're going to learn how to do this semester so that we could, in theory, make a model like this. So, we're going to do a simple version again, but a model like this for any chemical you want. Okay, so here's an even more simplified version of the world, and you're going to see this slide over and over again as we go through the class. Here I have divided the world up into 4 compartments. We have the air, we have the water, We have all the things that we're going to lump under a heading called octanol, which includes natural organic matter, biological lipids, solvents, all those kinds of things I'm going to lump under something I'm going to call octanol. And then you have the pure phase of the chemical, which could be either a liquid or a solid. And so what we're going to do in this class, the first thing we're going to do is talk about the partitioning of the chemical between its pure phase and the air, right? And the reason we do that is because in the pure phase, you have ideal behavior, or you can assume ideal behavior. And in the gas phase, we have something called the ideal gas law, because we can assume ideal behavior in the gas phase too. And so this, which is the vapor pressure of the chemical, is kind of the easiest place to start, because you have ideal behavior on both sides. And then we're going to get a little bit more complicated and start thinking about the dissolution of the chemical from its pure phase into water. So that would be its aqueous solubility. And then we'll start to talk about the partitioning between water and octanol. And that will basically complete our triangles. Oh, of course, also we're going to do our Henry's law constant, which is the partitioning of the chemical between the water and the air. And once we know that, we could, by inference, just figure out KOA and CSAT-O, which is, this would be the solubility of the chemical in octanol, and this would be the octanol air partition coefficient. Once you know how to do that stuff, then you're off and running. And these are all equilibrium constants. So we're thinking everything is being at equilibrium at this point. Later on the semester, things will start to not be at equilibrium anymore. But in the beginning, it's all at equilibrium. So the goals of this course are to give you the tools you need to understand and evaluate the fate of organic chemicals in the environment, both in a qualitative way, say, I think that thing's going to vaporize, and also in a quantitative way by actually calculating how much of the chemical will stay in the gas phase versus dissolve in water versus, absorb to carbon. And I like to think of this as developing your chemical intuition. Being able to just look at a chemical structure and have an intuition about what's going to happen to that chemical. So that means if we, for example, I've been doing this a long time, so I look at this chemical here. This is atrazine. It's a pre-emergence herbicide sprayed on the fields before the weeds emerge. That's why it's called pre-emergence. I can look at this and I can look at all of these nitrogens and I can say, this is a very polar chemical. Therefore, it's going to have a low vapor pressure. It's not going to volatilize very much. It's going to be highly soluble in water. So most of this chemical is going to stay soluble, which means that when you apply it to fields, there's a problem of runoff. That's something we're going to have to think about. Somewhat reactive. This chlorine might react. There might be some side reactions here at these different nitrogens. So this is a fairly reactive chemical. It's not going to persist for too long in the environment. I mean, it'll persist a while, but not forever. Here's malathion. I can look at this chemical and say, aha, right here, that's a phosphorus. That makes this an organophosphorus pesticide. Reactions happen right there at that phosphorus, so it's not going to be very long-lived in the environment, and I can predict what the reactions are going to be. Again, it's very polar because of all these oxygens and sulfur groups. All these things make it very polar. I'm sure you remember from organic chemistry that this is called an ester. This thing right here is an ester. Makes it reactive and relatively polar. Then I can also look at something like, here's a tetrachlorobiphenyl, a PCB molecule, and I can say, well, that's completely nonpolar. I don't see anything polar there at all. Not very reactive. Low vapor pressure, so that's mostly going to absorb to sediment and go nowhere. Here's phenol. I can look at that and immediately tell you that this proton right here is exchangeable. Could be lost, and you could get phenolate, the negatively charged anion. And the phenolate is going to behave very differently than the protonated, neutrally uncharged phenol. I can look at something like this is carbon tetrachloride, which is still used as a solvent a lot of times. I can look at that and say it's got a reasonably high vapor pressure. It's going to volatilize. It's going to react with UV light, and I can tell you what's going to happen, right? So I can look at these structures and I can get a decent guess at the Henry's law constant of the chemical. Again, that's water to air partitioning. I can have a reasonable guess at its octanol to water partitioning, which again, we're using octanol as a proxy for all of the organic carbon stuff in the environment. And then we can also make a good guess at its aqueous solubility, again, based on whether it's got these polar functional groups. And I can tell you something about its reactivity. And if I know these few properties, I can tell you an awful lot about the ultimate fate of this chemical in the environment. One of the ways that we figure out the actual numeric value of some of these properties is to use some estimation techniques, because all of the chemicals that are being produced haven't actually been evaluated to see whether they're toxic, which is sad but true. Unfortunately, it's better now because we have the Safer Chemicals Act. But in the 10 years ago, 20 years ago, there was no requirement that you had to test things for toxicity before you could start selling them and just disposing of them in the environment. And not only did you not have to know about toxicity, but you also didn't have to know it's Henry's Law. You didn't have to know KOW. You didn't have to do any testing on these things at all. And so rather than actually do these tests and use laboratory experiments to do things like measure Henry's Law, we want to be able to quickly and easily estimate them just based on structure. And so I'll teach you a lot about how to do that. The wild card, of course, is toxicity. I will not really talk about toxicity in this class. There's other classes that will give you lots of information about toxicity, but toxicity is very difficult to estimate, and so we're not going to really go there in this particular course. So I mentioned already that the first half of the class, things are going to be at equilibrium. We're going to be talking about equilibrium constants. And then in the second half of the class, we'll get away from equilibrium, and then things will start to be under kinetic control. So you can view the whole world as sort of a war between thermodynamics and kinetics. Thermodynamics is the determinant of where things are going to end up ultimately. At the end of time, when everything comes to equilibrium, this is where things are going to end up. But in the short term, things are not at equilibrium. And so we have to think about kinetics and ask ourselves, okay, well, I know eventually this chemical is going to end up here, but how long is it going to take to get there? And is that time frame reasonable compared to my time frame as a human being, right? I'm only going to live, I'm old, I'm only going to live another 40 years, maybe, if I'm lucky. You guys will live a lot longer than me. So I might not care too much about what happens to chemicals more than 50 years from now. On the other hand, I might care very much about what happens to chemicals 1,000 years from now. If I'm dealing with radioactive waste, I probably want to know what's going to happen to it 1,000 years from now. So you have to think about what your time scale is and ask yourself, do the kinetics support the idea that my chemical will reach equilibrium in that time frame? Or do I need to think not in terms of thermodynamics, but in terms of kinetics? So that's where the two things come together, where we start to make these box models. Again, that's kind of how we would calculate something like a TMDL. That's how we would calculate what the concentrations of the chemical are likely to be once it ends up in its ultimate state. So I do expect that you took organic chemistry. I recognize that many of you don't remember your organic chemistry very well. That's okay. That's why I organized the class into teams. Hopefully, every team will have at least one person who remembers their orgo. I do hope that you remember some of these phrases, like if I say this is a saturated bond or an aromatic bond, you know what I'm talking about. You remember something about oxidation states, you know what polarity is, hydrogen bonding. You can maybe name some of these functional groups, ethers and esters. Now, I promise you I will never give you a name and make you reconstruct the structure from the name. I would never do that. I am not cruel. I would always give you the chemical structure, and don't worry too much about the name. So I'm not, if you don't remember the difference between an ester and ether, it's no big deal. That's not going to be the end of the world. But it's not a bad idea to maybe go review some of this stuff. It wouldn't kill you. Heterocycles, electronegativity, things like that. Those are terms that I hope that you're familiar with. If they don't sound familiar, I suggest that maybe you want to read chapter 2, which we're skipping because it's a review. But if some of this doesn't sound familiar, you might want to read chapter 2. And of course, I assume that you remember your basic thermodynamics, free energy, enthalpy, entropy. We'll do a little review of that before we launch into any heavy-duty thermodynamics. But hopefully you remember the basics of how this works. So you have many, many wonderful resources. Your textbook, as you know, I have made it available to you free, which I'm not supposed to do, so don't tell anybody. But I made the textbook available for free, and it does have a lot of really useful information at the back. So, go leaf through those appendices. Those are very interesting. The notation, this book was written by a couple of people from Switzerland. René Schwarzenbach among them. Phil Geschwend is at MIT, but René Schwarzenbach was at EWAG. I think he retired now. And he's Swiss. So he's very precise. And they're very precise about how they do the notation. You'll notice there's just a gajillion superscripts and subscripts and stuff, and they're just trying to have everything just absolutely perfect. And so I have done my best to have the lecture notes use exactly the same notation as the textbook, just to try to avoid confusion. But it can be a little tricky sometimes, so just keep your eye on that notation. It can be very confusing. There's lots of wonderful online resources that we will talk about. This is one of the few classes where I'm going to tell you to use Wikipedia because, if you want to know about atrazine, you just go to Wikipedia and look up atrazine, and it will give you lots of useful information about atrazine. So actually, let's go do that real quick. Nope, I'll discard those. So if I go here to Wikipedia, and I just search for atrazine. I got a chemical structure here. I have a 3D structure. I've got the IUPAC name, other names. I've got the CAS number, lots of other useful information here. I got the chemical formula, molar mass, density, melting point, boiling point, solubility in water, all these wonderful things. And also tells you a little bit about how it's synthesized and, what's used for and all kinds, here's the whole metabolic pathway for atrazine. So Wikipedia can be very, very useful. I highly encourage you to use it. And then the other resource I have here is EpiSuite, which is supposed to be here somewhere, and I'm not seeing it, so my link sucks. Hey, where did it go? Where's EpiSuite? Predictive models. I'll have to get you a better link here. Anyway, let's do this the hard way. EpiSuite. There we go. That's much better. I'll have to provide you with this link instead. You can cite it. You can download it here. So this is free software provided by the EPA. And somewhere in all of this, there should be a place to download EpiSuite. Here you go, right here. You can download it. Only works if you have a PC. Sorry, EPA does not develop software for the Mac, unfortunately. But you can download EpiSuite. I have it down here. It's called EpiWeb. EpiSuite, same thing. It has all these different things in here. So here's how you predict KOW, melting point, boiling point, vapor pressure, water solubility, KOW, Henry's law, octanol air partition coefficient, organic carbon to water partition coefficient, bioaccumulation factor and bioconcentration factor, all kinds of cool stuff that you can do. And we will learn how to use this software a little bit in our class. But again, this is free. And if you go work for a consulting firm after you leave Rutgers or really anywhere, but you work for a consulting firm or whatever, and you are doing a project and you say, I got these numbers out of EpiSuite, no one's going to question you. They're going to say, okay, well, they must be good. So wonderful resources out there. Make sure you take a look at them. There's also some other stuff. There's other places you can get chemical information on the web. So as I go through, I will often use some shorthand and talk about different classes of chemicals. Like I might say BTEX. And so BTEX is this benzene, toluene, ethylbenzene, and xylene. These are components of gasoline, right? So, if you have a leaking, see, this is what happens when you try to use the pointer. The pen. There we go, pen. Here's BTEX. That's, if you have a leaking underground storage tank for fuel, for gasoline, that's what you're going to be worried about is BTEX. Chlorinated C1 and C2 compounds include things like perchloroethylene and tetrachloroethylene and dichloromethane. These are all used as solvents, and they're big environmental problems. PAHs are polycyclic aromatic hydrocarbons. PCBs are my favorite chemicals. They're what's putting my kids through college. I'm an expert on PCBs, so we'll talk a lot about those. If I say the word dioxins, that's a shorthand for polychlorinated dibenzo-P-dioxins and furans. I'm going to try to talk a lot more about PFAS this semester. In the past, I really haven't, because I'm certainly no expert on it, but I'm learning a lot more about it now. These are a big, big environmental problem, an emerging problem that you may very well encounter when you leave Rutgers. So we're going to try to talk about them some more this semester. Personal care products include things like pharmaceuticals and fragrances and disinfectants. Yay, triclosan. So all these things that you're using on your hands right now to avoid COVID fall under the heading of personal care products. So these are some of the acronyms I might use. If you hear me say them, I just want you to know what they mean. So that's where we're going to stop for now. There's actually more to this slideshow if you want to look at it. The PowerPoint is posted online. But this is a good place to stop for now. This is an introduction to what we're going to be doing in the class. And so I hope that helps, kind of give you a big framework, a big overview to help you understand how all the pieces fit together. And I'm looking forward to seeing you for the rest of the semester.